Before we dive into today's frozen mystery, make sure you hit that subscribe button and turn on the bell icon, because here on Strange History we uncover the forgotten technologies, lost discoveries, and unbelievable stories that shaped the world in ways textbooks never told you. Now, let's head north, into the kind of cold that makes metal scream. Picture a rifle in the Arctic dark metal steaming from the breath of men and machines, temperatures plunging toward -40 degrees Celsius, and ordinary gun oil thickening into wax. During those brutal winters, in polar patrols and icy campaigns, soldiers faced an invisible enemy: the cold itself. A frozen firing pin could mean the difference between life and death. Yet, among those struggling battalions, a few had a secret. An oil blend so unusual, so effective, that their weapons stayed smooth and reliable when everything else locked solid. This wasn't high-tech chemistry from a laboratory. It was a humble mix that smelled faintly of the sea and smoke, a blend of fish oil, graphite powder, and ethanol. Together, they formed a self-lubricating film that didn't freeze, even when exposed to Arctic blizzards. According to declassified cold-weather manuals, this mixture didn't just keep rifles firing, it saved entire missions, and decades later, it remains one of the most fascinating examples of natural chemistry meeting survival. Let's unpack the science behind this forgotten blend. The base was fish oil, which is rich in unsaturated fats that stay fluid at extremely low temperatures. Unlike mineral oils which stiffen as temperatures fall, fish oil maintains a thin, mobile layer that coats metal surfaces evenly. That layer not only lubricated but also repelled moisture, reducing frost buildup on moving parts. Then came the second ingredient: graphite powder. Graphite is made of carbon atoms arranged in sheets. Tiny layers that slide over one another like a deck of cards. It acts as a dry lubricant, maintaining smooth movement even when the oil itself begins to lose viscosity. Finally, ethanol was added, a volatile solvent that thinned the oil and allowed it to seep into the smallest mechanical joints before evaporating, leaving behind a slick frost-proof coating. In chemistry terms, this combination worked on multiple fronts. The oil displaced water and prevented condensation, the graphite reduced friction at the solid interface, and the ethanol ensured quick application and deep penetration. Together, they created a low-freeze lubrication system that was decades ahead of its time. In fact, the underlying principle, combining a liquid film with a solid lubricant, is still used today in aerospace, cryogenics, and precision engineering. Now, how did this formula come to be? Historical evidence points to early 20th century experiments in Scandinavia and Northern Europe, where engineers faced the constant problem of lubricating machinery in sub-zero temperatures. When World War II and later Arctic operations began, the lessons learned by fishermen, explorers, and local mechanics suddenly became military secrets. Field reports show that when standard-issue oils froze, improvised blends like this one kept weapons operational. Some manuals even hinted at organic oil mixtures distributed among select units for extreme cold operations, though details were often redacted or classified. The effectiveness of this blend wasn't just mechanical, it was psychological. Imagine being a soldier in the dark, endless cold, knowing your rifle might fail simply because the lubricant turned to sludge. The reassurance that your weapon would fire, no matter how cold it got, meant everything. This oil wasn't just chemistry, it was confidence bottled in a tin. But before you start picturing secret recipes and home experiments, let's make one thing clear. We're not here to teach you how to make weapon lubricants. Modern synthetic oils and dry films are far superior, safer, and environmentally regulated. What we're exploring is the history, the innovation born from necessity, and the chemistry that still inspires today's engineers. So why fish oil? Why not something else? The answer lies in biology. Fish that live in freezing oceans have oils rich in omega-3 fatty acids, unsaturated molecules that resist crystallization. In plain terms, they don't solidify easily. When used in machinery, that same property translates into low-temperature flexibility. Long before synthetic polymers, nature had already engineered the perfect antifreeze molecule. Add graphite, and the science becomes even more fascinating. Unlike most powders, graphite doesn't absorb water or become brittle in the cold. Its carbon layers can shear effortlessly, forming a micro-thin barrier that protects metal-to-metal contact. When combined with a small amount of oil, graphite forms a semi-dry film that continues to lubricate even when the oil film is wiped away or partially frozen. That's why modern dry film lubricants, used in spacecraft, firearms, and industrial machinery still rely on graphite and similar materials like molybdenum disulfide. Ethanol's role completes the picture. It was the delivery system, carrying the oil and graphite into every tiny crevice before evaporating. The result? A self-organizing protective layer that functioned like modern nanocoatings decades before nanotechnology even had a name. The chemistry community now calls such systems hybrid lubricants, blending organic and inorganic materials to achieve multifunctional properties. And it all started with something as simple as fish oil and graphite. When cold weather manuals were declassified in the late 20th century, references to non-thickening organic lubricant mixtures reappeared. Often cited as examples of field innovation that inspired later research into biolubricants. Today, we use eco-friendly lubricants in wind turbines, marine engines, and even robotics, many of which draw directly from those same principles, plant or fish-derived oils combined with microsolids for temperature stability. The past, it seems, had already found the blueprint for the future. But perhaps the most striking lesson from this story isn't chemical, it's human. In war or exploration, survival often comes down to ingenuity. When standard solutions fail, people innovate. The soldiers who mixed that odd-smelling paste weren't chemists. They were problem solvers under pressure. They didn't invent a new material, they rediscovered what nature already knew. And that's what makes this story so strange and so powerful. From the frozen battlefields of the Arctic to modern research labs, one truth remains. Sometimes, the simplest materials hold the greatest secrets. That humble fish oil blend reminds us that survival, science, and creativity often flow from the same source: curiosity. If you enjoyed this dive into forgotten chemistry and battlefield ingenuity, give this video a thumbs up, share it with a friend who loves hidden history, and don't forget to subscribe for more stories where science meets mystery. This has been Strange History, where the past is never really gone, it's just waiting to be rediscovered.